let's hypothesize that a relationship exists between electromagnetism and gravitational acceleration. However, electromagnetism is a broad reference, so we'll need to be a bit more specific. So, what specifically about electromagnetism might relate to gravitational acceleration, if at all? Since we can easily manipulate electromagnetic fields, we're actually talking about space-time engineering. As engineers, what proven tools can we draw upon to help us mathematically define the relationship between electromagnetism and gravity? Buckingham pi theory. But how does it work? Buckingham pi theory works by relating and scaling physical dimensions. So, the first step in the Buckingham technique is to choose the parameters which we consider relevant. This is a personal choice. No right or wrong selection exists. In our case, and in order to start building a solution, let's assume that gravitational acceleration depends upon the magnitudes of the magnetic field, electric field, position in space, electric charge, and the electromagnetic field frequency. The next step is to decompose the units of each parameter into a representation of mass, length, time and charge. Once this is complete, we can very easily write an equation relating all of our parameters together. We have generalized the solution in the greatest possible way by including an index with each parameter. Without these indices, we would be assuming a specific solution to the equation. At this point in the Buckingham technique, we need to keep everything as generalized as possible. Finally, we include an experimental relationship function. This is a parameter specifically intended to relate our theoretical solution to the real world, and is the most important inclusion into our generalized solution. With our general solution formulated, we may now express it in decomposed dimensional form. The letter x in the function denotes any and all potential influences in our equation, which have not been considered. For example, this might include temperature, quantum spin, materials of construction, or the texture of melted ice cream in the Amazon rainforest on a Tuesday afternoon. So, as you can now understand, the letter x represents absolutely everything which has not been considered. Next, we are able to very easily write down the index equations in matrix form, as shown. When we solve the system of equations, we find that x5 equals 0. This is a very important result because it affirms that electric charge evaporates from the solution. This means that any gravitational model inclusive of charge has been incorrectly formulated and may be ignored. Now, we are able to group terms and express the general solution in its simplest form. It is important to note that we have transitioned from 5 unknown indices to just one unknown index, x1. Lastly, we execute a simple dimensional check. If each pi group is dimensionless, then no formulation errors have occurred. With the general solution in its simplest form, the next challenge is to find solutions for x1. The first configuration of interest is the frequency domain. We would like to know how x1 behaves when the electromagnetic field frequency varies across an infinitely large spectrum of values. The first boundary condition occurs when the frequency tends to 0. In such a case, we see that x1 equals -2. Similarly, when the frequency tends to infinity, we see that, once again, x1 equals -2. For the purpose of clarity, we have substituted x1 equals -2 into the general solution, whilst maintaining pi groupings. In the same process, we have incorporated a frequency term into the experimental relationship function. This does not modify the function in any way, as it is not yet evaluated, but it signifies two key attributes. 1. That we have performed a mathematical operation on the general solution, involving frequency. 2. That the general solution has been simplified by incorporating the contribution of frequency into the experimental relationship function. Once again, starting with the general solution and repeating the previous procedure, in order to find solutions in the displacement domain, we see that x1 equals -1. In our next slide, we will investigate solutions for x1 involving transverse plane wave solutions in a vacuum. To apply the general solution to Maxwell's equations, the magnitude of the position vector must be interpreted as wavelength, when considering transverse plane waves. Performing two simple substitutions into the general solution, we obtain a value of x1, applicable to an infinitely broad frequency spectrum. Once again, as before, we incorporate variables into the experimental relationship function. As shall be demonstrated later, this equation shall become very important going forward. Let's now review our experimental relationship functions. By application of the forms obtained in the frequency, displacement and wave function domains, we may determine an ideal solution. By applying transverse plane wave limits to the frequency and displacement domain precipitations, an ideal solution for Maxwell equation applications is derived below. So, what conclusions can we draw from the derivations executed thus far? Firstly, we have utilized the Buckingham-Pi method to derive a general solution relating electromagnetism to acceleration. In doing so, we mathematically demonstrated that our initial inclusion of electric charge evaporated. This means that the form of acceleration derived is not related to Lorentz forces. Next, we found the ideal solution of the general form, relating the requirements of Maxwell's equations to acceleration. Following this, we employed Einstein's equivalence principle to finalize our interpretation of relating electromagnetism to gravitational acceleration. Therefore, we may summarize the following 5 points. 1. Gravitational acceleration at every point in 4D space-time may be represented by transverse electromagnetic plane waves, obeying a cubic frequency distribution. 2. During the derivation process, electric charge evaporated, excluding Lorentz forces. 3. We have inadvertently described the gravitational property of the quantum vacuum. 4. At the instant of the Big Bang, the universe may be described by a single wave function. 5. Most importantly, we have established a relationship between electromagnetism and gravity.